Yeah.
Okay, so we're going to go ahead and get started. So we are very happy today to have Karin Sandstrom visiting from the University of Arizona. Karin was a graduate student at UC Berkeley, where we overlapped briefly, and she got her PhD in 2009. And then after that, she was a postdoc at the Max Planck Institute in Heidelberg, where she worked with Fabian Walter. And while she was there, she won a very prestigious fellowship called the Marie Curie Fellow, which is awarded by the European Union. And then after that, she just recently came back to the States, so she's now at the University of Arizona as of this fall as the Bach Postdoctoral Fellow. The Bach Fellow is the University of Arizona Prize Institutional Fellowship, so also very prestigious. Karin's a multi-wavelength observer. She works on dust and gas and ISN in nearby galaxies. And today she's going to talk to us about star formation and the cold interstellar medium in nearby galaxies.
Well, thank you very much for the introduction, and thanks to all of you for the opportunity to visit San Diego, lovely weather, and tell you today about my work trying to understand the properties of the cold interstellar medium in nearby galaxies, and in particular, how efficiently it gets converted into stars. So to start off, I just want to acknowledge that this is work that's done as part of several large collaborations, and I have many collaborators on these projects. The first of these teams is the Kingfish team, which was a key program on Herschel to observe nearby galaxies, and that was led by Rob Kennicott and Daniela Calzetti. And then there's also the Things and Heracles teams, which are surveys of gas in nearby galaxies, led by Fabian Walter and Adam Leroy. And some of the people who played key roles in the work I'm going to show you today are highlighted here in blue. So to start, I want to spend a few minutes placing the work I'm going to explain to you in the context of the big picture question of understanding galaxy evolution. So when we look out at the universe around us today at a redshift of 0, and we see these populations of galaxies, the key question is, how do we explain their properties, their masses, their metallicities, their morphologies, and how and when they're forming stars? So to do that, we have a set of key ingredients that we can work with. First off is dark matter, which dominates the mass of the universe, and the interactions between dark matter structures set up the conditions where galaxies live. And so following the evolution of structure in dark matter is the first key part. After that is the supply of gas, and the various physical processes that determine how gas gets into a galaxy or gets back out and then maybe back in again and all that kind of crazy stuff that sets up how much gas you have to work with in a galaxy. And then there's star formation. So the process of taking that gas and turning it into the observable galaxy that we see out in the universe. So there's a variety of other aspects that come to play in this process, but the basic point is that to understand galaxy evolution, we have to combine all of these areas and have a good understanding of each individual one. So my work focuses on the last one there, star formation. So once you have a bunch of gas in a galaxy, how effectively does it get converted into stars? So throughout the talk, I'll refer to two very related quantities. First off, the star formation efficiency, which tells you the rate of star formation relative to the amount of gas, and then its inverse, the depletion time. And I'm going to kind of refer to these interchangeably, so I just wanted to introduce them. They're very simply just ratios that tell you how much star formation you get for a given amount of gas. So you can think of the depletion time in particular as the time it would take to use up all of the gas you have at the current rate of star formation. So the question I'm interested in is what environmental parameters control these numbers, and which large-scale properties of galaxies determine this star formation efficiency. So possible effects that may be important are the dynamical effects in the galaxy, its stellar potential, the metallicity of the galaxy, various other properties. So for the purposes of this talk, because I'm interested in these large-scale properties of the galaxy and how they affect star formation, I'm going to be measuring star formation efficiency on kiloparsec scales, essentially. So this has a number of advantages because if we were to look at each individual star formation region, it has a lifetime and an evolutionary path that goes from having a lot of gas and very little star formation to having only new stars and basically no gas. So if you catch it along any point of that evolution, you would get a different answer for the star formation efficiency. Yep?
Are you only looking at galaxies that are not in clusters?
Well, the current set of galaxies I have is not in clusters, but I hope at some point to have a much wider variety of galaxies, and that'll be something I talk about at the end of the presentation. So by averaging together a bunch of star-forming regions in a given kiloparsec of galaxy, what we hope to do is remove some of these stochastic effects and get at the underlying drivers for the star formation efficiency. So in many ways, this is complementary, though, to what we can do in the Milky Way, where we have many advantages in studying star formation. The first of those is that we can actually count up individual young stars to measure a star formation rate. And we have access to a bunch of different tracers of gas that we don't anywhere else. In addition, we have very high physical resolution, so you can study the star formation efficiency, for instance, of a single protostellar clump, or a core in a molecular cloud. So the stuff I'm going to talk about is on much larger scales and doesn't take advantage of these advantages that Milky Way has. And on the left here, I'm showing what you can do in the Milky Way. This is a plot that from Lombardi, Lada, Lombardi, and Alves that counts up the number of YSOs in a given molecular cloud and looks at that versus the cloud mass. So you can see how effectively a given cloud is forming stars. So the Milky Way, though, while it has many advantages, from the perspective of trying to connect star formation efficiency to galaxy evolution, has quite a lot of limitations. Namely, that the Milky Way just does not have the range of conditions that we need to cover in order to connect star formation to the overall galaxy population. And in fact, the Milky Way may not even be particularly representative of galaxies in the local universe that are forming stars right now. So this is a plot from a recent paper by Much et al., where they've taken a simulated population of galaxies for the Z of 0 universe that matches up very well with what is observed. And they isolate galaxies in their simulation that are spirals, that have the same stellar mass approximately as the Milky Way, and compare the star formation rates. And what you can see, this is a star formation rate on the y-axis, is that the Milky Way falls quite low, actually, compared to the rest of the star-forming galaxies, even at Z of 0. So in order to really span the range of conditions we need to do to connect star formation efficiency with galaxy evolution, we have to expand beyond the Milky Way. And the first step in doing that is looking at nearby galaxies. So I'd like to spend a few minutes next telling you about how we measure star formation efficiency in nearby galaxies. And the first problem is that we have to measure the star formation rate. We can't, like in the Milky Way, we can't actually just count up individual young stars to get a star formation rate. We have to do something slightly more indirect. And what is done is to use the aggregate emission in UV wavelengths or the aggregate emission ionized gas emission to infer the number of young stars in the star formation rate. So what I'm showing here are 3 galaxy SUVs that illustrate some of the relevant wavelength ranges. A key problem, though, with using these optical and UV tracers of star formation is that they're extincted by dust and get re-emitted in the mid and far infrared. So what I'm going to be using is a technique that people have developed to combine UV and optical star formation rate tracers with mid-infrared hot dust emission. So there's a hybrid calibration that tries to take into account both the obscured and unobscured star formation. So all of the star formation rate maps I will show use this sort of technique. So next, what we need to do is trace gas. And we have to worry about the various phases of gas that a galaxy has. To start, there's atomic gas, which is quite straightforward to trace. We just use the 21 centimeter line of atomic hydrogen and can map out where atomic ISM is. Molecular hydrogen is a much different story, and a lot of this talk is going to be devoted to how we trace molecular hydrogen and why that's interesting. And for the most part, ionized gas is negligible, and I'm not going to worry about it. So the first step in trying to understand star formation efficiency in nearby galaxies is to plot the total amount of gas and the total amount of star formation. So that's shown here from the classic well-known work by Kennicott in 1998. And each of the points on here, aside from the ones labeled centers, are entire galaxies. And what Kennicott found is a nonlinear relationship between the gas surface density and the star formation rate surface density. What that means is that when you get to higher gas surface densities, you have more effective star formation, essentially. The star formation efficiency gets higher as you go to higher gas surface densities. So one key question that's worthwhile to ask about this plot, though, is what does it mean to have the star formation efficiency for a whole galaxy at once? So if we look at one of these points, what you might see is something like this. Here, blue is tracing gas. 3.6, the green is tracing old stars, and the red is tracing new star formation. And what you might see is that there's a bunch of gas in this galaxy that's not really forming many stars, and then there's some gas that's forming plenty of stars. And so the question is whether a single galaxy on this plot tells you more about the distribution of gas in the galaxy or about the star formation that's happening. So in order to get at the actual star formation side of things, we need to resolve the galaxies and do this on much smaller scales. And there have been a number of surveys with the goal of doing that over the last decade, and I'm going to show you some results from a few of them, and just wanted to mention that there's a lot more that I will not be pointing out. But here are some of the surveys that tried to resolve the distribution of gas and star formation in nearby galaxies. First off is THINGS, which is the H1 Nearby Galaxies survey, which was led by Fabian Walter and used the VLA to map the distribution of atomic hydrogen in nearby galaxies. This was followed up by the Heracles survey, which is the Hera CO line emission survey, led by Fabian Walter and Adam Leroy. And this uses carbon monoxide to trace the distribution of molecular gas, which I will talk about again shortly. To get at the star formation, I'm going to be using observations from the SINGS survey, Spitzer Infrared Nearby Galaxies survey, which mapped this emission from hot dust at 24 microns and a variety of other wavelengths. And here are some of the images from that. And in addition, the GALEX Nearby Galaxies survey, which maps the UV emission that we can relate to these young stellar populations. So when you have all these maps and you can look at the resolved star formation efficiency in nearby galaxies, what you see is something like this. So this is work by Frank Yale in 2008, and what he did is to plot the same axes as Kennicott here, so gas surface density versus star formation rate, but now these are individual kiloparsecs of galaxies. And what they found is that the depletion time, or the star formation efficiency, is not a simple function of the total gas mass surface density. So as you go to lower gas mass surface densities, your efficiency drops off pretty steeply. So to first order, we actually have a very good explanation for why that is, and you can see that by dividing that plot up into atomic and molecular gas. So what's shown here is a plot from Andreas Schruba's work in 2011, although this has been a very heavily studied area of astrophysics, so many authors have come to the same conclusions. What you see is that the star formation rate surface density is poorly correlated with the atomic gas, but is quite correlated with the molecular gas, with a characteristic depletion time of something like 2 gigayears. So what this suggests is that the process of forming the molecular gas and the process of turning that molecular gas into stars can somewhat be separated. So the process here I'm interested in is the step that goes from molecular gas to stars. So this process up here, though, of creating molecular gas out of the atomic ISM is also really interesting, and be happy to chat with anyone at various meetings about the directions to go in studying that. But for the rest of this talk, I'm going to focus on this last step exclusively. So every time now I refer to depletion time or star formation efficiency, it'll be specifically for molecular gas.
Presumably this is, all of your information must be very metallicity.
That's true. Although, so H2 formation is very dust dependent, and that is also related to metallicity, yeah.
In your previous slide on the right side, molecular gas versus the points that are scattering above that kind of ridgeline, is there something different about those?
I will be talking a lot about that very shortly.
Okay.
All right. So now looking specifically at the molecular gas depletion time. These are the results from the recent paper on the Heracles survey. And what's plotted here is the H2 surface density versus star formation rate surface density. And in general, to first order, the nearby galaxies observed with Heracles are very well characterized by a molecular gas depletion time of 2 gigayears. There's a lot of disagreement, though, still in the community about the exact slope of the relationship between gas and star formation. So some people think that this is a superlinear slope. Some people actually think it's sublinear, too. There's a lot of recent work about sublinear Kennicutt-Schmidt law. Some people think it's linear.
What's the dotted line? Is that linear?
Yeah, dotted lines are linear.
Those are constant depletion.
Constant depletion, yeah. So regardless of the exact slope of this relationship, people tend to agree that in the disks of nearby galaxies, the characteristic depletion time, regardless of the details of the slope, is something like gigayears, 2 gigayears-ish. But that's not always the case, and there's some really interesting exceptions. So when we look at galaxies that are huge starbursts driven by the mergers of 2 galaxies, so ULERGs, or their high redshift counterparts, submillimeter galaxies, what people see is that there is a depletion time that's something like 5 to 10 times shorter than what you see in the disks of nearby galaxies. So that's very interesting. And also, when you look at nearby galaxies that happen to have low stellar masses, so these are dwarf-type galaxies with low metallicities, you also find this depletion time falling below the standard 2 gigayears. So I want to pose 2 possibilities. Either this is real or this is not real. If it's real, we would like to understand why these 2 starburst galaxies or low-mass galaxies form stars more efficiently. But the possibility exists that this is not real, and that one of the issues is we have not yet traced molecular gas properly. So I want to spend a little time now telling you about tracing molecular gas, and I hope that I will convince you that you should worry deeply about something called the CO to H2 conversion factor. So, tracing extragalactic gas, as we said before, H1 is easy, but molecular hydrogen is not. And that's because in the conditions where molecular hydrogen exists, it's not warm enough, really, to excite its rotational levels effectively. So it's almost invisible, for the most part, in the places where molecular clouds exist. So we're forced to use something else to trace molecular gas, and that has tended to be carbon monoxide. It's the second most abundant molecule. It has very bright rotational transitions in the millimeter part of the spectrum, and it's easy to observe. So what is done is to take the intensity of the CO line and convert it into a mass surface density, or mass, or whatever you'd like, of molecular hydrogen. And to do that, you use something called the CO to H2 conversion factor. So I'm going to use this number in mass surface density units and call it alpha. You may be more familiar with it as X. This is the same thing. And in the local area of the Milky Way, it's been measured that this number is around 4 solar masses per square parsec per this funny radio astronomer unit of Kelvin kilometers per second. So the question, though, is, for applying to extragalactic objects, how much does this vary? Can we actually use this conversion factor we found nearby us in the disk of the Milky Way? And in order to answer that question, we have to measure alpha CO in other galaxies and in different conditions. And that is kind of tricky. So there's 4...
How do you measure it in the Milky Way?
A lot of these techniques I'm going to discuss right here are the way that it's been measured in the Milky
In other
Way.
words, if you were to put error bars on the Milky Way, how big?
Factor of 2-ish in the disk of the Milky Way, at least. Okay, so the ways that you could attempt to measure alpha CO are kind of limited because the whole game is finding out H2 independently of CO. So you have to measure H2 masses, and that's not so easy. One way you could do it is if you think that molecular clouds are virialized objects, that is, they're supported against their self-gravity by turbulence, you can measure their sizes and their velocity dispersions and calculate their masses. And that's the initial way that this CO to H2 conversion factor was sort of approached. However, that is a quite strong assumption that many people do not agree is correct, that clouds are not actually clearly virialized. Additionally, you need to get very high resolution in order to measure this size outside of the Milky Way. And up until recently, that's been a bit of a challenge. Another way you can attempt to do this is using gamma rays. So gamma rays result from the interaction of cosmic rays with ISM gas. So if you have some idea of what the distribution of cosmic rays are in the galaxy, and you observe the gamma rays, you can invert this and work out the gas distribution. Unfortunately, with the current technology and what seems to be the case in the near future, it's really hard to observe these gamma rays anywhere but the local group. And even the nearest local group galaxies are pretty difficult. But this has been very effective at constraining alpha CO in the Milky Way.
And do they find the factor of 2 that you mentioned from that method? Or?
The factor of 2 uncertainty?
Yeah.
That's sort of the combined uncertainty, I would say, from a bunch of different methods.
Does the dynamics one assume any star formation? You know, stars are supernovae inside the cloud.
No, I don't think so.
So it's dead inside the cloud.
Well, it's turbulent inside the cloud, but yeah. Mm-hmm.
The gamma ray observations are not viable because the modeling is very poor on the spatial distribution and correlation with gas.
That's true. It's a big assumption to say you know the distribution of cosmic rays. That is not something that's easy to work out. And I have a plot later on that shows that, actually. Another way you could attempt to do this is by observing the optically thin isotopologues of CO, so something like C18O. And if for some reason you know how abundant the isotope should be, or could be, and you measure the amount of C18O, you can convert that into H2. Problem there is these are very faint lines and have been difficult to detect outside the Milky Way. So one other way you could attempt to do this is with dust. And if you have some idea of the dust to gas ratio, then you can work out how much gas there is if you observe the dust. And the problem with this one has been in the past that in other galaxies, the infrared observations that you need to constrain the amount of dust have had very low angular resolution. So you would get 1 point for an entire galaxy, for example. But that's not the case anymore. Thanks to the excellent wavelength coverage and resolution of Herschel, we can now attempt to approach constraining alpha CO in other galaxies using dust. And I'd like to show you now some of the work I've done recently on just that problem. So the whole game of constraining alpha CO using dust is based on this equation, where you connect the observables, so the CO intensity, H1 surface density, and dust surface density, with these two numbers, dust to gas ratio and alpha. So the basic idea is you put in some assumption for this number, and you work out what alpha CO is. And so one thing you could do is just fix it if you think you know what dust to gas ratio should be. Or you could try to, observe a region of a galaxy that has no molecular gas and just measure the dust to H1 and get it that way. But neither of these techniques really work very well in other galaxies. So I want to tell you about how you can do it by measuring both simultaneously. And this is a pretty straightforward thing that's just facilitated by the angular resolution of Herschel. So what I'm going to do is assume that dust to gas ratio is constant on a kiloparsec scale. I'm going to put in no assumption for its value, just that over about a kiloparsec of a galaxy, it should be the same. And we have a region of a galaxy here that's about a kiloparsec in size, where we have many individual measurements of these quantities. So what you can basically do is just generate a set of equations for each point in that region that connects the dust to gas ratio and alpha. And then if you say that all of these should be the same, you can just solve a coupled set of equations and get alpha. So in practice, there's a bunch of different variations on this technique you could use to measure alpha. And if you're interested in how effective they are, you can consult this paper where there's an extensive appendix that I'm sure no one has ever read. But that's the basic premise. And just in case anyone would like to have a more visual illustration of how this works, this is a little cartoon that shows it. So if you take these points in this region here, some points will have more CO relative to H1. They'll have more molecular gas relative to atomic, and some will have less. And those points with less will be very insensitive to whatever you do to alpha. So they're down here on this plot, and they stay put regardless of what you say alpha is, because they care mostly about the H1. Up at this end, the points care very deeply on the dust to gas ratio about what alpha is. So when you adjust it, they move like this in this plot. And at some point, you get to an alpha value where essentially all of the points in your region have the same dust to gas ratio. And that's when you know you've gotten alpha right. So I'd like to show you the results of doing this for a number of galaxies and what we've learned about how to trace molecular gas this way. So the dust surface densities I'm going to use come from combining the data sets of Kingfish and SINGS. And between these two surveys, we've covered the essentially full infrared SED from 3.6 microns all the way out to 500 microns. So we have coverage of the entire black body peak of the dust in equilibrium, as well as the non-equilibrium dust emission at shorter wavelengths. And here's a pretty picture showing all of the Kingfish galaxies, 3-color imaging. And you can see that at the longest wavelength shown here, which is 250 microns, which is well on the tail of on the other side of the peak of the black body, we can resolve galaxies in great detail. So to get the dust mass, we model the pixel by pixel SED using Drain and Lee models. So here's the coverage with Spitzer, and here's the coverage with Herschel. And by doing this SED modeling, you can try a variety of different ways, and it's not particularly sensitive to the fitting technique you use on this peak of the black body. You can get out the dust mass. So the details of that are described in a paper by Gonzalo Añano in 2012. So as I mentioned before, I'm getting H1 from the THINGS survey and CO from the Heracles survey. So there's a subset of galaxies covered by all of these surveys that I'm going to use in the following. So let me show you some results. This is NGC 628, and overlaid on these images, I hope you can see all of these little circles. So these circles are the regions inside of which we've done the solution. So there are resolved measurements inside those regions. So here's what the results look like. The first panel to focus on is the middle one. This shows where the good solutions are. Black is good. Some of the solutions fail, maybe because they don't have enough contrast in CO to H1.
So are the circles large compared to the point spread function of the telescopes?
Yes, it involves quite a few resolution elements in there. So this is the alpha map over here, and the Milky Way value is somewhere around this cyan and green color. And you can see that wherever there's a good solution in this galaxy, it's basically that color. So we can look at this in more detail by plotting it versus radius. And this green strip here is the uncertainty on what I would consider the disk value in the Milky Way. So that's this green strip. And all of the good dark measurements here, the black points, where we have a good solution, for NGC 628, agree pretty well with that range. So that's nice. We're pretty confident the Milky Way value works okay for 628. But that's not always the case. Here is NGC 6946. Similar face-on spiral, same distance, very different answer. So in this case, in the center of the galaxy, which I'll plot here, it's a little easier to see, the conversion factor drops below the Milky Way value by a large amount, so factors between 5 and 10. So that's a big change, and even in a lot of the other outer radii of this galaxy, there's a difference. So I want to summarize the whole sample, what we found, with this kind of complicated plot, but I will explain the different panels. Up at the top, the gray points are each individual measurement from the overlap of these 3 galaxy samples. This is their radial profile, so this is alpha versus radius. And then down at the bottom, I've normalized by each galaxy's average. And I want to point out a few important points about this plot. First off, the average radial profile is quite flat, and it's relatively consistent with the Milky Way value, just slightly lower. But it's not just a flat radial profile. There's very clear evidence that in the centers of galaxies, alpha tends to be lower, so lower than the galaxy average, and also lower than the Milky Way value substantially in some cases. So you can see up here that a good subset of these galaxies have conversion factors in their centers that are well below the Milky Way value. So it's worthwhile to note that I've been saying the conversion factor measured in the Milky Way disk, but the same exact thing is actually happening in the Milky Way. So when you go to the center of the Milky Way, you find a very different conversion factor. This is I can't remember, you asked about gamma rays. This is the plot of what you get when you try to do the conversion factor as a function of radius with gamma rays. And these various weird offsets here are because no one knows what the distribution of cosmic rays should be, right? This is different models. But they do all agree in the center. So in the center, gamma rays, dust, C18O, everything agrees that it's much lower. So maybe we should not have been surprised to see that a bunch of other galaxies similar to the Milky Way have this low conversion factor. So the question of what's going on, though, that makes this happen is the thing that I'm most interested in right now. And I've got several different approaches to try to understand that. And there's some intriguing results that I want to show you that are still very new. And so this is not cooked through all the way yet. But the exciting part is that we seem to see that excitation of the molecular gas is playing a key role. So what this is two spectra from the Beyond the Peak survey, which was a Herschel program using the Spire Fourier transform spectrograph to get the spectrum between 200 and 600 microns of a bunch of kingfish galaxies. And what you see here is NGC 6946, that one I showed you, that has a very low central alpha, and 4254, which is normal. And you can immediately see by looking at these that there's a difference in molecular gas excitation. This galaxy, you can see up to CO 10 to 9, which is kind of rare for nearby galaxies. And in general, we see this trend in a bunch of these centers with a low conversion factor. So something is happening with the excitation. It's not clear if that's the cause or a side effect of whatever is driving this. And that's the focus of a lot of what I'm doing right now.
So this is exciting transitions in the rotational bands
Of CO, yeah.
So I'm looking at a higher temperature, effectively.
Sorry, I wasn't paying attention to the scale before. When you're talking about the center of the galaxies, what scale are you talking about?
It's on the order of kiloparsecs. Kiloparsec or a couple of kiloparsec radius.
And does that mean, I forget which way the alpha goes, that means there's less molecular hydrogen than you expect from the CO2?
Yes,
CO1?
exactly.
And are most of these galaxies, what fraction of these have AGN? Or?
The Kingfish and Sings galaxies have pretty weak AGN. Some of them do have evidence for AGN in the center. And I think that, well, I'm not 100% sure exactly which fraction of the ones that have low alpha have AGN, but it wasn't everything. There were clear exceptions. It was like some AGN galaxies have totally normal alpha in their center, and some have, it didn't have a good predictive capability. Okay, so I wanted to change subjects for 1 second and show you what we learned about dust-to-gas ratio from this procedure. So if you recall, I didn't put in any assumption about what dust-to-gas ratio was, just that it was constant on a kiloparsec scale. And what we got out is a nice proportionality between the metallicity and the dust-to-gas ratio. So this, is the subset of galaxies where I can make this plot is actually kind of limited because most galaxies don't have measurements of their internal metallicity gradients. But for the ones that do, we get a relatively nice proportionality with something less than a factor of 2 scatter. So the cool thing in terms of tracing molecular gas that this lets us do is that we can try another approach to measuring alpha that lets us go outside of the region where this first one applied. So what I've told you about so far requires good signal to noise on CO in order to do this solution. But in the outskirts of galaxies, CO gets quite faint, so we don't really have the signal to noise to push out there. But if we can say we know what the dust-to-gas ratio as a function of metallicity should be, then you can just invert this equation to measure alpha. So I've been working on that lately, and this is a plot showing some results from that procedure. And what you see is that as you go towards lower and lower metallicities, alpha starts to increase. And it gets quite high, in fact. And this is not something that's new. This has been observed in a lot of different situations, in particular in the local group. So these green points are local group galaxies from Leroy et al. 2011. And you can see that alpha CO is increasing quite steeply as you go towards lower metallicities. So the two lines that are overplotted here are two models that attempt to explain why that's the case. And I think at this point there's a relatively good agreement about physically what's happening that's driving this. And that is that as you go towards lower metallicity, what you end up having is less dust shielding for your molecular gas. And the CO cares very deeply about dust shielding. It can be photodissociated by UV photons. And the H2, there's so much of it, it shields itself. So it's basically insensitive to the amount of dust shielding. So as you go towards lower metallicity and your dust shielding drops, what happens is that you dissociate the CO and end up with a bunch of H2 that has no CO. And this is the CO dark H2 that is very big topic of discussion these days because people would like to use CO at high redshift to trace things that have low metallicity, but you have to start to worry about your CO being just photodissociated. So the effect,
that ties the dust directly to essentially to the metallicity.
Right.
Right. So the higher the metallicity, the more dust you're going to make.
Right. I mean, there's a lot of complexities of that issue, which
that's probably, where's the dust come from, right? So
exactly, and it's not totally clear that it should be dependent on metallicity. We happen to find that in these, big nearby spirals, but if you go to real low metallicity galaxies, the dust content appears to be very sensitive to the star formation history and the processes that have produced and destroyed the dust. So this proportionality with metallicity is not a given. Right, so the effect on alpha from this process is that you have to represent more H2 with less CO emission, so your alpha increases. So just to summarize, I'm sure you're getting sick of hearing about alpha, maybe, but what we've learned so far about tracing molecular gas is the following. In the disks of normal nearby galaxies, the Milky Way value appears to work all right. In the inner kiloparsec of galaxies, though, it's not working all right. Alpha is much lower. And in the outer regions of galaxies that have low metallicity, alpha is much higher. So the typical practice of taking a whole galaxy and applying a single conversion factor is not a good idea. I think that's what this demonstrates.
Is this true independent of the stellar mass of the galaxy, the little ones and big ones?
Well, I mean, if it's a low stellar mass galaxy and it's more dwarf-like, it will tend to have lower metallicity, and so.
So if you factor that, what I'm asking is, if you factor that out, if you take a dwarf galaxy that has normal metallicity into the disk, would it be like a normal alpha, or maybe?
That's a really good question. I don't know the answer to that. I mean, what is a dwarf galaxy? That's a really good question. So we do have dwarf galaxies that have normal metallicity, and they tend to be tidal dwarf galaxies, things that are made up of the stuff that was stripped off of another galaxy by an interaction. And I don't know what the answer is to that, whether alpha would be the same, because it's possible that some of the effects in those galaxies, like the lack of pressure from a stellar bulge, for instance, or the different turbulence, because this is not the same sort of dark matter potential. Yeah, that's a really good question. I don't know the answer to that, but that would be an interesting direction to go. Okay, so I'd like to switch now to telling you about how this impacts our understanding of star formation efficiency, now that we've seen that you have to be a little careful about how you trace molecular gas. So before we talked about low metallicity galaxies having higher star formation efficiency, shorter depletion times, but it turns out that almost all of that effect can be explained by the fact that we underestimated the amount of gas using a standard conversion factor. So when you use one of these metallicity-dependent, dust-to-gas ratio-dependent conversion factors, you find that they have depletion times that are very similar to the standard 2 gigayears. And the same is also true in the SMC. So this has been done in great detail. What's shown over here is what you get for this is contours of point density showing the star formation versus molecular gas if you use the Milky Way alpha CO. And it would be characterized by a very short depletion time, something like a tenth of a gigayear. But if you use an alpha measured from dust, you end up getting these points over here and then smoothing them to lower resolution to compare with other galaxies. You see basically the standard 2 gigayear timescale. So the star formation efficiency does not appear to be different in these. It's just that we need to trace gas more carefully. When we look at the full population of Heracles, you see this characteristic depletion time again. But now that we are being more careful about the centers of galaxies, where you have low alpha, something interesting starts to happen. So you start to see a population of points that have a much lower depletion time in the centers of galaxies. And I'm right now trying to understand what's going on in those regions, and there is something very interesting that I'd like to talk to anyone about who's interested in galaxy morphology and rearranging gas. So this is that same distribution of points from Heracles, And these points here are the subset of galaxy centers where we have really nice measurements of alpha CO. And these are face-on galaxies to avoid any issues with gas at different radii being included. And one of the key factors that determines where a galaxy center sits in this space appears to be whether or not the galaxy has a stellar bar. So there's a very clear offset in the star formation efficiency for galaxies that have bars. It's higher. And the question is why, and I don't have a full answer for you yet, but it may have to do with packing all of this gas into narrow lanes that are feeding into the center. You get much higher gas densities and maybe turbulent effects on the clouds, and it's a really interesting correlation that I think is going to be exciting to investigate over the next couple of years. So the other interesting thing about those galaxy centers is that when you compare that higher star formation efficiency with what we've seen in this two sequences, that offset in star formation efficiency puts them in the same category as ULERGs and merger-induced starbursts. So it may be the case that these nearby galaxy centers are a place where we can study molecular clouds in detail in order to try to understand what properties bring about this enhanced efficiency. So just to summarize what we've learned so far, using an improved assessment of H2, we can reveal changes in the star formation efficiency. Namely, in the centers of galaxies, it's much higher. We can also show that in low mass galaxies and low metallicity conditions, it seems to be pretty normal for the most part. So the open questions and the things I'd like to address in the future are the following. What drives the variations of this conversion factor? And crucially, how can we predict what number we want to use for a given observation? Right? So CO is going to continue to be the workhorse molecular gas tracer at a variety of redshifts. And if the conversion between that and H2 is varying substantially, we need to have a way to predict what is appropriate value to use. Second, what environmental factors are causing these changes in the star formation efficiency? And then the important thing that I'll talk about in just a minute is how can we connect what we've learned about star formation efficiency to the overall population of galaxies. So, to start, understanding the variations of alpha CO. The things we need in order to do this are high-resolution observations that look at individual molecular clouds in regions where alpha is varying. And we need to study them in lines other than just 12 CO. We need to look at these phaser lines, optically thin lines of CO, other tracers of molecular gas, and try to understand the properties of the gas there and what's changing. We also want to make sure to take into account if there's any gas actually that's not confined to molecular clouds. There may be some molecular gas that is in the more diffuse medium. So the three requirements for an observation that would let us do this are high angular resolution, high sensitivity, and full coverage on angular scales. And the good news is that all of that is now possible with ALMA. So ALMA is the Atacama Large Millimeter Array. It's an array of 66 antennas that work at millimeter and submillimeter wavelengths located at high altitude in Chile. It's in cycle 2 of observations, so this is still early science. And the design of ALMA is such that it's sensitive enough to observe CO from a Milky Way-like galaxy at Z of 3 in less than 24 hours. So this is a very, very powerful telescope array. And just to illustrate that the stuff I would like to do is certainly feasible with ALMA, I'd like to show you some early science observations from the center of this galaxy, NGC 253, which is a nearby starburst galaxy. So this was observed with ALMA in cycle 0 with 16 antennas for a couple of hours. So this is a tiny fraction of the full capability of ALMA. And what you see here are 50 parsec, or sometimes even more, higher resolution maps of a variety of different molecular gas tracers in the center that resolve individual clouds and let you study the properties of those clouds. So this is early science and was just a tiny capability fraction of what ALMA will be able to do at full operations. Just to follow up on that, one of the things that I'd like to do in the next year or two is to point ALMA at some of the regions where we found this low conversion factor. So for instance, the center of NGC 3351, shown down here. And what we just proposed is to look at C18O in 2 different transitions and measure the amount of molecular gas from those lines. So this direction is, I think, the clear way to head to try to measure, to find out what's changing about alpha and be able to predict when we should use different values of alpha for our observations of galaxies across the universe. So having done that, I think the next key step is to try to connect what we learn about star formation efficiency to the full galaxy population at Z of 0. So right now, the galaxies where we can study star formation efficiency are a strange, highly biased subset of the galaxies that exist in the local universe. These are everyone's favorites. They tend to have names like the whirlpool or something like that. So this is not a representative set of galaxies. So in order to do that, we need to have a careful sample selection that fully samples statistically the population of galaxies in the local universe. And with that, if we make a survey of star formation efficiency, so including star formation rate maps and molecular gas maps, should be able to see in what step of galaxy evolution the changes in star formation efficiency are affecting things. So if star formation is much more efficient in galaxy centers, for example, is that driving the morphological evolution of some types of galaxies? So in order to do this, the three requirements are clearly defined sample selection, statistical properties as well, millimeter interferometry to measure the H2 distribution, and then kiloparsec resolution measurements of star formation. And I'd like to suggest that this is a very straightforward thing to do in the future with some of the large optical integral field spectroscopy surveys that are going to happen. So optical IFU observations map the full optical spectrum at sort of 1 to 2 arcsecond resolution for the whole disk of galaxies. This is some test observations from the SDSS-3 MANGA project, which is a survey that's going to cover 10,000 galaxies with fully sampled IFU maps. And from these observations, we can get star formation from H alpha and H beta, so extinction-corrected star formation, metallicity diagnostics, stellar population, all sorts of other observations of the environment. And luckily, both MANGA and another large optical IFU survey called CALIFA have very clearly defined samples. So, for example, this is the CALIFA parent sample shown in blue, which they've taken some care to relate to the Sloan Digital Sky Survey Z of 0 galaxy population. So you can take the properties you learn from CALIFA and work back to, what exactly the full population of galaxies is experiencing. So both of these surveys cover a lot of galaxies. MANGA is going to cover 10,000, and it will start observing in fall of 2014. And what I would like to do is follow up these IFU surveys with molecular gas observations using millimeter interferometry. And it's not particularly the case that this has to be done with ALMA. It can be done with smaller interferometers as well, because you're not needing to, go to like ridiculously high resolution. Most of the time, a compact configuration is fine. You don't need the crazy sensitivity to detect lots of other lines. So I think this is going to be a very fruitful direction to head over the next several years, trying to understand how variations in galaxies, star formation efficiency variations, affect their evolution. So just to keep in mind, though, that doing that at Z of 0 is very informative, and we will learn a lot of things. But if we are interested in galaxy evolution, most of the star formation that happened is not happening now. So most of the star formation will have happened at a much higher redshift. And really what we'd like to do is the same sort of study, but at Z of 2 or 3. And that is also going to be possible. So ALMA and the Very Large Array can already map CO in galaxies at high redshift. This is a plot that shows where the different CO lines redshift into various bands from ALMA and Plateau de Boer in the VLA. And with the next generation of telescopes, so JWST in space and the 30-meter telescope on the ground, the near IR and mid-IR IFU instruments will be a very effective way to make the maps of these star formation and metallicity tracers that we use in the local universe, but next at high redshift. So, to conclude, I would like to leave you with a couple of take-home points. When H2 is properly traced, we can reveal a lot of interesting variations in the star formation efficiency, even in nearby galaxies. And these variations will hopefully let us learn about what process controls star formation on those on galaxy scales. And finally, the future is very bright for expanding this study to inform our knowledge about galaxy evolution, both in the local universe and at high redshift. So, thank you very much.
Have you tested your constancy over a kiloparsec by using larger and larger fields of view to see if it stays constant?
So what you're saying is taking the nearby galaxies, doing a kiloparsec, then bigger and bigger and bigger. Right, so we have done that, and the thing that happens is that you end up averaging out, these variations in alpha on small scales. So if you include a lot of gas and you make this a really big region, what happens is that you can get a solution, but it's the solution that's representative for a gas at a bunch of different radii.
But you can test by just checking by the nearby little circles. You're saying
Yeah.
it's constant on top of a kiloparsec. Well, if that's true, then the one next to it
Oh,
should be
I see.
very
You're talking
close.
about dust to gas ratio. Yes, we get a very consistent result. I don't know if I can go backwards to that, but the maps of dust to gas ratio that come out are very smooth. I was
The
actually
assumption's
showing,
okay, that
yeah,
constant over kiloparsec.
yes.
That's
Yes, that was very reassuring that it's self-consistent, that solution.
So can you get isotopic information at relatively high redshift?
Yeah, I think you can actually with ALMA. So it'll be difficult. I mean, you can detect these high redshift galaxies in plain old 12 CO in many hours of observing at high redshift. But for very bright things, you can do it now. There's one paper recently, I can't remember the author, that had looked at a lensed galaxy and measured a variety of different CO isotopes using, it wasn't even ALMA, I think it was Plateau de Boer or something like that. So that is definitely possible to do.
Any other questions?
Can Planck, I'm sure you know the Planck recent CO measurements across the whole spectrum, even the 853. Is there anything that's useful for subtracting backgrounds or?
Yeah, well, it's definitely useful. I mean, it's always great to have a full sky map of CO from, whatever technique you can. And so I think they get one of the higher JCO lines too. So the standard, Milky Way map of CO was done with the CFA telescope on the roof, which I got the chance to operate as an undergrad. That was fun. But having these higher JCO line maps is really useful as well. So that, I think they cover 3 to 2 in the.
Oh, definitely.
Mm-hmm. Yeah. So that is useful to understand the excitation of the different clouds, and you could potentially try to relate any variations in alpha to the conditions, that are varying with excitation. Mm-hmm. So yeah, the Planck maps are really cool. It's very exciting.
Back to your alpha discussion. If you had a given mass or surface density of CO, what would determine the intensity of the CO?
So from a molecular cloud, the CO emission is optically thick. So the main parameters that determine the emission are the velocity width that you get to play with in order to fill it up with CO emission, and the temperature of the cloud. So the key parameters for optically thick CO emission are what the velocity structure of the cloud is like and what the excitation conditions are.
Do you know about those things?
Well, for the observations I've been working on so far from Heracles, we don't really have the resolution spatially in order to say what the cloud velocity dispersions are, but that's something that will be straightforward to do with ALMA. And the excitation of CO is a really interesting subject. So you have to take care to model the heating sources throughout the cloud, and how the density determines how the levels are populated. So people tend to do this with things like large velocity gradient models. And that's another subject that's very exciting lately, because we have all these measurements from Herschel of high JCO molecular lines, so up to 10 to 9 and higher, like I showed. And modeling the full spectrum of those lines reveals some interesting facts about CO excitation and how it depends on density and various things. So
It must be complicated to figure out how you excite actually collisional excitation or.
Right. In some regions of the cloud, it's not dense enough to fully populate the levels, so you end up with this subthermal excitation. And in some regions of the cloud, it is thermal, and so it is a complicated subject. to understand. So that's why I can't just say for sure that this observation that the CO ladder is enhanced in these centers means that's what's changing alpha, because there's a variety of different conditions that are coming to play, different densities, and you have to be very careful about modeling that. So. Mm-hmm.
Do you see any imprints from spiral structure in this alpha maps?
We do, and maybe I can go back and show you later. For that map of 6946, you can actually see some hints of spiral arms, which is something that's very interesting. You don't see that in any of the other galaxies that I've looked at, just 6946, which is a kind of an odd galaxy in some ways. It's forming a lot of stars, and it has these magnetic field structures that people have been investigating along the spiral arms that maybe contribute to changing alpha in some way. I haven't looked very deeply into that question, but there are some hints that that's there, yeah.
Okay, let's thank Karin again.
Yeah.
Okay, so we're going to go ahead and get started. So we are very happy today to have Karin Sandstrom visiting from the University of Arizona. Karin was a graduate student at UC Berkeley, where we overlapped briefly, and she got her PhD in 2009. And then after that, she was a postdoc at the Max Planck Institute in Heidelberg, where she worked with Fabian Walter. And while she was there, she won a very prestigious fellowship called the Marie Curie Fellow, which is awarded by the European Union. And then after that, she just recently came back to the States, so she's now again at the University of Arizona as of this fall as the Bach Postdoctoral Fellow. The Bach Fellow is the University of Arizona Prize Institutional Fellowship, so also very prestigious. Karin's a multi-wavelength observer. She works on dust and gas and ISN in Nearby Galaxies. And today she's going to talk to us about star formation and the Cold Interstellar Medium in Nearby Galaxies.
Well, thank you very much for the introduction, and thanks to all of you for the opportunity to visit San Diego with lovely weather, and tell you today about my work trying to understand the properties of the cold interstellar medium in nearby galaxies, and in particular, how efficiently it gets converted into stars. So to start off, I just want to acknowledge that this is work that's done as part of several large collaborations, and I have many collaborators on these projects. The first of these teams is the Kingfish team, which was a key program on Herschel to observe nearby galaxies, and that was led by Rob Kennicott and Daniela Calzetti. And then there's also the Things and Heracles teams, which are surveys of gas in nearby galaxies, led by Fabian Walter and Adam Leroy. And some of the people who played key roles in the work I'm going to show you today are highlighted here in blue. So to start, I want to spend a few minutes placing the work I'm going to explain to you in the context of the big picture question of understanding galaxy evolution. So when we look out at the universe around us today at a redshift of 0, and we see these populations of galaxies, the key question is, how do we explain their properties, their masses, their metallicities, their morphologies, and how and when they're forming stars? So to do that, we have a set of key ingredients that we can work with. First off is dark matter, which dominates the mass of the universe. And the interactions between dark matter structures set up the conditions where galaxies live. And so following the evolution of structure in dark matter is the first key part. After that is the supply of gas, and the various physical processes that determine how gas gets into a galaxy or gets back out and then maybe back in again and all that kind of crazy stuff that sets up how much gas you have to work with in a galaxy. And then there's star formation. So the process of taking that gas and turning it into the observable galaxy that we see out in the universe. So there's a variety of other aspects that come to play in this process, but the basic point is that to understand galaxy evolution, we have to combine all of these areas and have a good understanding of each individual one. So my work focuses on the last one there, star formation. So once you have a bunch of gas in a galaxy, how effectively does it get converted into stars? So throughout the talk, I'll refer to two very related quantities. First off, the star formation efficiency, which tells you the rate of star formation relative to the amount of gas, and then its inverse, the depletion time. And I'm going to kind of refer to these interchangeably, so I just wanted to introduce them. They're very simply just ratios that tell you how much star formation you get for a given amount of gas. So you can think of the depletion time in particular as the time it would take to use up all of the gas you have at the current rate of star formation. So the question I'm interested in is what environmental parameters control these numbers, and which large-scale properties of galaxies determine this star formation efficiency. So possible effects that may be important are the dynamical effects in the galaxy, its stellar potential, the metallicity of the galaxy, various other properties. High physical resolution, so you can study the star formation efficiency, for instance, of a single protostellar clump, or a core in a molecular cloud. So the stuff I'm going to talk about is on much larger scales and doesn't take advantage of these advantages that Milky Way has. And on the left here, I'm showing what you can do in the Milky Way. This is a plot that from Lada, Lombardi, and Alves that counts up the number of YSOs in a given molecular cloud and looks at that versus the cloud mass. So you can see how effectively a given cloud is forming stars. So the Milky Way, though, while it has many advantages, from the perspective of trying to connect star formation efficiency to galaxy evolution, has quite a lot of limitations. Namely, that the Milky Way just does not have the range of conditions that we need to cover in order to connect star formation to the overall galaxy population. And in fact, the Milky Way may not even be particularly representative of galaxies in the local universe that are forming stars right now. So this is a plot from a recent paper by Much et al., where they've taken a simulated population of galaxies for the Z of 0 universe that matches up very well with what is observed. And they isolate galaxies in their simulation that are spirals. So for the purposes of this talk, because I'm interested in these large-scale properties of the galaxy and how they affect star formation, I'm going to be measuring star formation efficiency on kiloparsec scales, essentially. So this has a number of advantages, because if we were to look at each individual star formation region, it has a lifetime and an evolutionary path that goes from having a lot of gas and very little star formation to having only new stars and basically no gas. So if you catch it along any point of that evolution, you would get a different answer for the star formation efficiency. Yep.
Are you only looking at galaxies that are not in clusters?
Well, the current set of galaxies I have is not in clusters, but I hope at some point to have a much wider variety of galaxies, and that'll be something I talk about at the end of the presentation. So by averaging together a bunch of star forming regions in a given kiloparsec of galaxy, what we hope to do is remove some of these stochastic effects and get at the underlying drivers for the star formation efficiency. So in many ways, this is complementary, though, to what we can do in the Milky Way, where we have many advantages in studying star formation. The first of those is that we can actually count up individual young stars to measure a star formation rate. And we have access to a bunch of different tracers of gas that we don't anywhere else. In addition, we have very high